Hello everyone, I would like to talk about my work on the use of deep learning to simplify the clinical workflow for the use of ultrasound to assess pleural effusion. So this work is a collaboration with partners from the Gondar University Hospital in Ethiopia. Ultrasound imaging allows earlier identification of pleural effusion and a grading of its severity, which allows better treatment allocation. So this can have many consequences, particularly for the fight against tuberculosis, of which pleural effusions are a major symptom. However, it needs a lot of expertise, and in many low and middle income countries, there is a shortage of skilled sonographers who can perform this task. And even for experienced sonographer, it's still a challenging task, which is made difficult by many issues, such as the fact that the lungs can change appearance in ultrasound images. So the primary goal of our work is to demonstrate the feasibility of deep learning methods to tackle the pleural effusion segmentation task. So our first contribution is using the state-of-the-art NN-unit deep learning model to address this task, and our second contribution is to investigate the use of spatial context information by extending the NN-unit model to use coordinate convolution. So, all ultrasound images were acquired using a SonOS X7 ultrasound imaging by an experienced radiologist at Gondar University Hospital in Ethiopia. We have a total of 143 images that were acquired from 59 different patients. These images were obtained at the left and the right post-lateral alveolar and subscrotal views with linear array and curved array ultrasound probes. So the data were split according to the use of these two probes into two different datasets, one using 51 images and the other one using 92 images. We also have annotated this image at the time of acquisition to measure the extent of the effusion, and this acts as a ground truth segmentation for the training of the model. Before being used for training and evaluating the models, each image was automatically cropped using a rectangular cone mask to remove non-imaging content. And next, we applied an impacting text algorithm using Carass OCR, followed by a template matching and age detection algorithm from OpenCV to remove the annotations that were added previously to the image to measure the effusion. All the images in both datasets were manually segmented using the IACL software by a trained observer, and these segmentations has acted as ground truth for training and evaluating the proposed model. Additionally, we ask a second trained observer to perform independent segmentation of subsets of 10 random images, each from two datasets, and these 10 random images were used to compute an estimate of inter-observer variability in the manual segmentation process. So for our baseline model, we employed the NN-unit deep learning framework, and we used the two-dimensional implementation, and we also trained the model for 100 epochs to limit the computational demand. We also investigated whether using coordinate convolutions could improve the performance of the NN-unit baseline. Coordinate convolutions work by adding extra channel to the input layer, which contain the coordinates of the pixels. So in our case, as we have two-dimensional images, this involved adding two extra channels, one containing the I coordinates and one containing the J coordinates, with the coordinates being specified in pixels and the origin being at the top left of our images. So the evaluation for both experiments was performed using a 5-fold cross-validation, which means that the data were split into 5 folds and each was held out in turn and evaluated on a model trained using the 4 other folds. So Due to the large variation in appearance between images acquired from the same patients, we performed the cross-validation splits at the image level rather than the patient level. And because NN unit performs hyperparameter optimization using heuristic rules and not using the validation data, and because we used the model from the last epoch rather than using the validation data for model selection, these cross-validation results can be considered as independent test results. So all the models were evaluated using the dissimilarity coefficient, and additionally we computed measures of the error and the bias in estimation of effusion area, since there are really likely to be clinically important measurements in the effusion assessment process. Finally, we also compute the DSC between the manual segmentation of the two observers on the subset of 10 images for each dataset, and the median DSC are reported as estimates of inter-observer variability in the manual segmentation. So it can be seen that despite having fewer images, the baseline model for linear datasets obtained a higher median DSC than the model for the curved datasets. So for the first dataset, the coordinate convolution model improved the DSC and has reduced the area error and the bias. We did a two-tailed Wilcoxon signed rank test, and we found that the difference between the baseline DSC and that of the coordinate convolution model was found to be statistically significant for the first datasets, but there was no significant difference for the curved array datasets. It's interesting because for both datasets, both baseline and coordinate convolution models has performed better than the estimates of the inter-observer variability. However, we can note that the inter-observer variability is quite high, which is likely to reflect the difficulty and the partly subjective nature of the effusion segmentation task. Therefore, it seems likely that the deep learning models are learning to segment effusion in the style of the main observer, which may not always be consistent with the second observer. So, to the best of our knowledge, we have demonstrated the potential of deep learning for pleural effusion assessment. We had a baseline model who had a performance superior to that of our inter-observer study, and the coordinate convolution has improved performance in one of the datasets. Why did not improve performance on the other one dataset? We think that because of the geometry of the image, because the second dataset was a dataset composed of curved image, maybe using polar coordinates, which improve results on the training of these datasets. In addition, we also think that different aspects of the effusion could potentially be recognized using this type of deep learning models, which is in the goal to reduce the need of skilled operators in low and middle income country. Also, one limitation of our work is the lack of control case in our database. All the subjects in the database had effusion identified clinically. Expanding the datasets to include case with no pleural effusion will enable to have a more robust model to be trained. And also because, as we said, that manual segmentation can be subjective, having a whole group of observers trying to reach a consensus of where the effusion lies could reduce the uncertainty and the variability in the assessments between the observers.